Dr. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing double integration method for finding the slopes as well as the deflection of simple supported beam when it is subjected to point load at its center as well as the eccentric. This content belongs to. In order to find the slope as well as the deflection of the beams, two methods are applicable. One is the double integration method. The second one is the McLeod's method. The double integration method is the most suitable for finding deflection as well as the slope of the beam when it is subjected to single or the multiple loads. Here, McLeod's method is the most suitable to find the deflection as well as the slope when the beam is subjected to several loads. According to the double integration method, the bending moment at any point is given by the equation m is equal to Ai into dy by dx square. Now, this integrating these equations, we got to Ei into dy by dx is equal to integration of m, and one constant is also obtained. We are calling it as C1 values. The C1 value is obtained by applying end condition of the beam. So, by using these equations, we got that is slope of the beam now. Again, integrating above equations once again, we got I is equal to double integration of m plus that is C1 into y. Again, one more equation we will get the C2 values. The C1 values and C2 values, these are the first integration as well as second integration constant. This can be evaluated by using the end condition of the beam. So, from this relationship, it is obvious that the first integration is useful for determination of slope, the second integration is useful for the determination of deflection of the beams, and the C1 C2 are representing the integration constant which can be evaluated by using the end condition of the beam. Here we are considering simple supported beam subjected to W, the two point load at its center as shown in figure. Let AB is representing the length of the beam and W is the point load which is acting at a point C, that is center of the beam as shown in figure. Here for finding deflection as well as the slope, always the reference point should be here the B. From B point only we have to consider the distance x in order to determine the slope as well as the deflection. So now you are considering a point x, capital X, at a distance of x as shown in figure. Here before finding the bending moment at a section x, it is required to determine the values of reactions at A and B as shown in the figure. Since the beam is in equilibrium conditions, that means the sum of the forces which are acting in vertical direction should be equal now. That is the should be equilibrium. That means the sum of the forces which are acting downward direction should be equal to the sum of the forces are acting upward directions. That means here now, according to this figure, RA plus RB, these are the reactions at A and B. It should be equal to the vertical load W as shown in figure. Since the load is acting at the middle now, generally we will having this RA plus RB is equal to W by 2 now. It can be evaluated again now by using one more equations now. This RA and RB both are unknown quantities. This is nothing but fundamental equations I use now. But we can take RA plus RB is equal to W and taking moments at any point, that is nothing but if I take sigma moment at A is equal to RB, which is the force nothing but acting at B, the reactions, multiplied by L. It should be equal to the moment created by the load at C, that is at a distance of L by 2 from A as shown in figure now. That is it should be equal now. From this relationship we got to RB is equal to W by 2 now. But according to relations, RA plus RB is equal to W. That means RA is also equal to this W by 2 now. So by using these relations, the magnitude of RA and RB be equal, which is equal to W by 2 now. Now considering distance x from B as shown in figure, which is represented as x capital X, the bending moment at this point is given by, since only one single force is acting toward the right hand side of the x now, hence the bending moment is equal to force into distance. We can take it as mx is equal to RB into x. This is nothing but a plus sign we are taking because the effect of this force is in the form of sagging. Hence, again integrating these equations, we got mx is equal to, we are having mx is equal to EI into d2 by dx square. Hence, doing this integration once again now, EI into d2 by dx square, we got it is equal to W by 2 into x as shown in a figure now. Integrating these equations, we got one more constant is known as a integration constant. That is EI into d2x by dy square is equal to m. M is equal to W by 2 into x, it is a positive value. Just integrating this equation number 1, we got EI into dy by dx is equal to W into x square by 4 plus C1 now. Where C1 is the integration constant, it can be evaluated by using the end conditions. Here when x is equal to, here now L by 2, we are having that maximum bending moment at its center. When the maximum bending moment is there, the slope at that point should be equal to 0 now. That means the dy by dx is equal to 0 in equation number 2 when x is equal to L by 2 now. By using this relationship, we got 0 is equal to WL square by 16 plus C1, or C1 is equal to minus of WL square by 16 now. To substitute these values in equation number 2, I got EI into dy by dx is equal to WX square by 4 minus WL square by 16 now. This is the required equation for determination of slope at any section from B as shown in figure now. The maximum slope is occurs at A and B. Thus, x is equal to here 0 position now in the equation. Hence, at B, if it is represented EI into dy by dx, which is equal to IB, it can be written as minus of WL square divided by 16 now. The minus sign means here representing the tangent at B makes an angle of WL square by 16 EI in negative or in anti-clockwise directions now. So IB is equal to, here now, IB is equal to IA, which is equal to, both are equal because of its geometry now. Or by putting x is equal to L in equation number 2, we got again IA is equal to WL square by 16 EI now. These equations are used for determination of the slope at A and B, and its value is 0 at the center where it is having maximum bending moment. Integrating equation number 3, once again now, we got EI into Y, it is equal to WX cube divided by 12 minus WL square by 16 into X plus C2, where C2 is the second integration constant now. Here EIY now, where Y is representing the slope of the section, but the slope is equal to 0 at A and B, and it is having maximum value at its center now. So when you are putting this X is equal to 0, that means Y is also equal to 0 in these equations. That is, here Y is equal to 0, when X is equal to 0. From this equation we got to C2 is also equal to 0 now. That is the integration constant to second one is 0. So the modified equation of fourth is, we can write now EI into Y is equal to WX cube divided by 12 minus half of X into ML square by 16 now. This is the required equation for determination of deflection of the beam at any section when it is subjected to point load at its center now. The maximum slope is generally occurs when X is equal to L by 2. So, by substituting the value of Y by 2 in the equation X by 2 in the equation number 5th, we got maximum deflection, that is known as the Y value. So, from this equation, EI into YC, because that is obtained only at the midpoint where the point load is acting. Here EI into YC, it is equal to, on substituting X is equal to here L by 2, we got WL cube divided by 12 into 8 now, minus of here X is equal to L by 2, WL square by 16. From this equation we got WL cube divided by 12 into 8 minus of WL cube by 13. On simplification we got this value is equal to minus of WL cube divided by 48 now. YC is equal to, from this equation we got WL cube divided by 48 EI. This minus sign is representing the deflection of the beam is in downward direction. Here the problem based on here the simple supported beam with the central load. A simply supported beam of length 3 meters is subjected to central load 10 kilonewtons. Find the maximum slope and deflection of the beam. Take I is equal to 12 into 10 to the power of 6 mm to the power of 4 and E is equal to 200 gigapascal. Here I am taking this is the beam is given, simple supported beam. Here these are the supports at A and B now. The length of the beam is equal to L, which is equal to, according to the problem, 3 meters is given. The load is acting at its center, as in this is equal to W now. So just I am taking the what are the given data in the problem now. A simple supported beam of span 3 meters. That is the length of the beam is equal to 3 meters is given. We are converting all the dimensions into mm only, because here I values is given in mm. We are converting into same units. That is 3 meters is equal to 3 into 10 to the power of 3 millimeters. The central load is equal to 10 kilonewtons is given. Here W is equal to 10 kilonewtons, which is equal to 10 into 10 to the power of 3 newtons. And the moment of inertia is equal to 12 into 10 to the power of 6 mm to the power of 4 given. And modulus of velocity is equal to 200 gigapascal, that is 200 into 10 to the power of 3 Newton per mm square. The maximum slope of the beam that is occurs at the A or B position, both are in equal magnitude values, which is obtained IA is equal to WL square divided by 16 EI now. Because according to our problem we required find the maximum slope and the deflection now. The maximum slope is obtained at A and B, that is where the simple supported beam is supported, and maximum deflection that is occurred at the midpoint of the beam, that is where the central load is acting, which is equal to 10 kilonewtons. So the maximum slope is equal to the equation is WL square by 10 to the power of 3 Newton per, here now mm square is given. A maximum slope is WL square by 16 EI, where W is equal to 10 and L is equal to 10 to the power of 3 now. 3 into 10 to the power of 3. L square is equal to whole square. W is equal to the load is given 10 kilonewtons. 10 into 10 to the power of 3 divided by 16 is given. E is equal to Young's modulus, which is equal to 200 into 10 to the power of 3 Newton per mm square. So these values we have taken here, these two values, and I is equal to area moment of inertia, which is equal to 12 into 10 to the power of 6 mm to the power of 4. Just substitute the values here now. Finally, we got on doing the calculations 0.0023 radians. This is the slope of the beam at A and B, both are equal in magnitude. The maximum deflection of the beam occurs at the midpoint of the beam, which is equal to y is equal to WL cube divided by 48 EI now. So where W is representing the central load, which is acting 10 into 10 to the power of 3 newtons. L is equal to length of the beam, that is equal to 3 into 10 to the power of 3 mm. 48 E means here Young's modulus, which is equal to 200 into 10 to the power of 3 Newton per mm square. I is equal to area moment of inertia, which is equal to 12 into 10 to the power of 6 mm to the power of 4. Then substitute the values in this equations. Here we got it is equal to 2.3 mm. This is the deflection of the beam now. The second problem, a wooden beam 140 mm wide, 240 mm deep, has a span of 4 meters. Determine the load that can be placed at its center to cause the beam of deflection of 10 mm. Take E as 6 gigapascal. Here the beam is given like this, assume it is in the form of rectangular shape. It is given. Again, it is in the form of, assume this is simple supported beam and so on. A wooden beam, but here the dimension is given, it is in the form of, here the side view it is given. Here 140 mm, it is the wide, and this height is given, it is called deep now, it is equal to 240. That is nothing but the rectangular shape is there in cross section, which is in the form of, here it is equal to 240. Here width is equal to 140, it is equal to 240. Here we require this moment of inertia of this cross section about its neutral axis, which is equal to, here I is equal to, we can take it as here 140 into 240 cube divided by 12. We have to determine this additional value for this because we require I value. First of all, we are taking what is the given data in the problem. The width of the beam is given 140 mm. Depth is given 240 mm. Span length is given 4 meters. 4 meters nothing but it is equal to the 4 into 10 to the power of 3 millimeters. Central deflection is given 10 mm. And modulus of velocity is given 6 gigapascal, which is equal to 6 into 10 to the power of 3 Newton per mm square. Let here W is representing the magnitude of the load which is acting at its center. The moment of inertia of this section is given by BDQ by 12, which is equal to 140 into 240 cube divided by 12. And doing this calculations we got, it is equal to 161.3 into 10 to the power of 6 mm to the power of 4 now. The deflection of the beam at its center is given by the equations yc is equal to wl cube divided by 48 e I now. So yc is equal to the maximum deflection which is permissible according to this problem is 10 mm equal to w. Here determine the load is required, hence w values we have to determine. Assume it is equal to w at its center, w into here 4 into 10 to the power of 3 whole to the power of cube, that is the wl cube now, divided by 48 into e, that is the young's smallest. Already we have taken it is equal to 6 into 10 to the power of 3 Newton per mm square, and this is known as here now I is equal to moment of inertia, area moment of inertia 161.3 into 10 to the power of 6. So from this relationship we got W is equal to 10 divided by 1.38 into 10 to the power of minus 3, which is equal to 3.75 into 10 to the power of 3 newtons, or it is also equal to 3.75 kilonewtons, that is which can be kept at the center of the wooden beam, so that the deflection is equal to the 10 mm. And derivation now, it is regarding simple supported beam with an eccentric point load. Here consider simple supported beam AB of length L carrying an eccentric load W at C as shown in figure. Here the eccentric load means the load which is not at all acting at the geometric center now. That is the C is earlier we have taken center now, but it is acting at a distance of C now. Here assume that location according to the problem is acting between A and midpoint M now. From the geometry of the figure we got, first of all we have to determine the reactions at A and B now. Here RA is equal to, assume this reaction at A, and RB is reactions at B we are taking, and W is acting at a distance of B from B position and small a at A position, such that A plus B is representing the length of the A plus B is representing the length of the beam now. Since the beam is in equilibrium conditions now, hence sigma Fx should be equal to 0, sigma Fy is also equal to 0, and sigma M is equal to 0. That means the sum of the forces which are acting on the body along the x direction should be equal to 0. Since in this problem there is no forces are acting in horizontal directions, hence the equation number 1 is not applicable. The second equation is sigma Fy is equal to 0. That means the sum of the vertical forces equal to 0. That means the sum of the forces which are acting in downward direction should be equal to the sum of the forces acting in upward directions. Hence, here we can take it, here W is acting in downward direction. So, the reaction forces at A and B, that is the RA plus RB is acting upward directions. From this relation got to RA plus RB is equal to W now. And one more is the moments created by these forces at any point should be equal to 0 now. So by using, we can take it now. The moment we can take, assume this according to this, if I take moment at a point A, it is equal to, we can take it as RB, the reaction force at B into L. It is acting in clockwise directions. If I take it as a positive, minus, that is the moment created by the W into A, it should be equal to 0 now. So here now first equation, the vertical force is nothing but RA plus RB is equal to, we can take it as a W now. By solving these two equations, RA plus RB is equal to W, one equation. The second one is RB into L is equal to W into A. And solving these equations, we got RA and RB values now. So on doing this calculation, we got to the reaction set A is equal to RA is equal to WB divided by L, and the reaction set B is equal to RB is equal to WA into L now. First of all, determine the reactions at A and B now. A case 1 we are taking now. Consider section X in a CB at a distance of X from B as shown in figure now. Here we are taking the point here now. The C is the point at which the load is acting now. But we are always considering the points with respect to the end B only. That is preferably in this case from the right hand side now. So at a distance of X we are taking now. Considering that is nothing but the point, what is the X point is lies between the reaction force at B, that is the RB, and the load is acting at C now. That is between B and C we are considering now. According first case 1 now. So the considering at X at a distance CB, at a distance of X from B as shown in figure, the bending moment at this section is equal to, as in Mx, which is equal to RB into X now. Here it is a positive because of that effect of this force here when deflate the beam in the form of sagging. So from this relation we got to RB is equal to WA divided by L. Here X is nothing but the distance between the considered point X from the B now. So from this point we got to WA divided by L into X now. This is nothing but bending moment created by RB at a distance of X now. Hence, this value can be represented as Mx. According to the bending equations, we got to EIE into d2y by dx square now. That is bending moment at any section X is given by EI into d2y by dx square. That means EI into d2y by dx square equal to WA divided by L into X now. Okay, these equations when integrating in the first time, we got the slope of the beam now, that is the divided by dx, plus one constant is also obtained. This constant is called the first integration constant. It can be evaluated by applying the condition of the beam. Similarly, here, on putting this here now, one condition now, when X is equal to B now, when X is equal to B, that is nothing but here point B, or here X is equal to L, that is known as here now the slope at a point to A position. According to the here end conditions, the slopes at A and B should be, it is there, which is equal to here now, when X is equal to B, we can take it as where C1 is representing here the first constant integrations now. When X is equal to here now B, that means it is equal to the point C where the load is acting. We got it EI into IC is equal to WA divided by L into B square by 2 plus C1. Where C1 is equal to, just on solving these equations we got here EI into IC minus WA square divided by 2 L now. Okay, substitute the values of C1 in previous equations we got EI into dy by dx is equal to WA into L x square by 2 plus EI into C minus the constant is also given WA square divided by 2L now. That is integrating above the equations once again to get the deflection of the beam. That is here EI into y is equal to, we got to WA divided by L x cube divided by 2 into 3 plus EI into IC, that is nothing but slope at a section C where the load is acting, multiplied by here x minus of WA B square into x divided by 2L plus one more constant we are getting, that is the C2 integration constant. Again, according to the geometrical construction, the deflection of the beam, simple supported beam is 0 at A and B. That means when x is equal to 0, that is the y is also equal to 0 now. That is substituting the values now. When x is equal to 0, this quantity is equal to 0. It is also equal to 0. It is also equal to 0. Here y is also equal to 0. From this relation we got to C2 is equal to 0 now. So the modified equation for the deflection of the beam is E I into y is equal to WA by L x2 by 6 plus EI into IC into x minus of WAB square into x divided by 2L. The equation second and fourth, that is the fourth equation, this is the second equation. So both are useful to determine the slope as well as the deflection of the at any section of the beam. These equations are applicable now if you know that is the slope of the beam at a section IC known value. Okay, based on this problem, just we are taking here one problem now. A beam of uniform section of span L is simply supported at its ends. It is carrying a point load of W at a distance of L by 3 from one end. Find the deflection of the beam under the load. A given span is equal to L, that length of the beam. Here point load is equal to W, and distance between the point load and the left hand is given here L by 3, 1/3 of its length. The distance between the point load and the right hand is the remaining values is 2L by 3 now. The deflection under the load is given by, according to the previous equations we got, WAB divided by L square minus A square minus B square divided by 6EIL now. Where A is representing now, if I take here is the beam of simple supported beam. Here load is acting W at its position now. This length is represented as B now. This is represented as A. Total length of the beam is equal to L is given. So on substituting these values in this equation we got it is equal to 0.0165 WL cube divided by EI now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.